Hello, I'm Jean-Philippe Delhom. I'm the CEO and founder of Delhom Acoustic. Today I'm going to talk about acoustic design and how it can enhance learning environments. So I'm very glad to be part of this knowledge sharing project. So Delhom Acoustic is an acoustic consultancy I founded 25 years ago. We are based in Europe and China and Asia in general. So acoustic is our expertise. So today my presentation will be split in 4 main parts. First, I would like to introduce the perception of noise in China. I will go through very quickly about acoustics, some acoustics basics. Then the main part of my presentation will be about acoustic in learning environment. And then at the end, I will give you a very short summary of key highlights. So noise in China, I wanted to talk about this because when we arrived in China a few years ago, many people told us that people don't care about noise. China is very noisy, and they were wondering how we could work in this country. And I would like to show you that this is not true, and I will prove it to you. And we have this annual survey from the Ministry of Environmental Protection of China, showing that noise pollution is the second main environmental concern among Chinese people, just after air pollution. So this means that people are complaining about it and are aware about the noise pollution. And there is also from this same survey, this information showing that people are complaining about it officially, because this is the number of official complaints that that have been recorded by the authorities about noise. So clearly, China is aware of noise issues, and maybe if we are still facing so many issues, noise issues in China, it's probably because people don't know we can do something about it. And I'm going to talk about how we can deal with these issues in learning environments. So acoustics in learning environments. In fact, when we design a new school or refurbish an existing one, most people will think about design, will think about the ventilation and heating systems, of course the room layout, sometimes the lighting, but quite often they will forget about noise and acoustic comfort. And this is quite surprising because there are many surveys showing that noise and acoustic comfort is very important in schools and in general learning environment. So there are many surveys, many facts that are proving it. So I will go very quickly on some of them. For example, this survey showing that every time we increase the noise, the background noise in a classroom, students in language and maths science their scores decreased by 5.5 points out of 20, which is quite a lot, and showing the importance of background noise, for example, in classrooms. There are also this survey showing that 60% of class activities involves speech between students and teachers or between students. So it means that the communication, the clarity of sound, the clarity of speech is a very important part if we want to get a good speech, good transmission of information in the classroom. So there are many examples from surveys showing the importance of this comfort. So what are the key areas for acoustic comfort in schools and learning environment in general? There are, I would say, all the spaces are very important. Classrooms, of course, the canteen, the music room, the theaters, even the social area, the gyms, we know can be very noisy, and the library, which is a very important space in the learning environment. So I will go through some of them today to show you what are the issues and what we can do to solve them. them. So first, the classroom. So there are three main issues in the classroom that can disturb the learning process. So the distractions from outside of the classroom, the speech intelligibility, and of course the background noise from technical equipment. So distractions. So it's the noise that can come from outside the room. It can be outside of the building, but also from another space inside the building. So for example, here, it's a modelization we did for a project school in Shanghai, where we have two main roads with high traffic that were or would impact the project. So we did a simulation of the noise to see how each facade could be affected. And then this helped to design the proper facade insulation. Without this type of simulation, in fact, we wouldn't know how many decibels we need to control and what could be the noise inside the building. So this helped to get the right insulation, so to use the right windows, the right glazing, save money, and because we avoid over treatment and reach the targets. So this is some tools we use designing the facade insulation to avoid the distraction and control the noise inside the rooms. We have also the internal insulation between spaces. So here is an example between two classrooms. So very often when we are addressing the issue of the insulation between two spaces, most people will think about the noise through the partition wall, and they will sometimes use a very complex or heavy, thick and expensive partition wall. But at the end, most of the time it doesn't work because noise doesn't travel in one direction. It can go through lateral transmission, through the facade, can also go through defect, like in this example, electric sockets. So at the end, even if we spend money on the partition, high performance partition, we won't get the right results. So what we need to do when we address this issue is to design properly the partition wall, and most of the time it will be a thinner and less performance partition, cheaper. But in the same time, we need to address all the defects like the junctions, control the noise going through the lateral transmission, through the defects, and then we can get the proper insulation. So it's not a question of only of performance of the partition wall, but it needs to be addressed in the globality of the transmission of noise. Speech intelligibility. So this is a very important part and an important issue in the classroom, because so what is speech intelligibility? It's the capability of understanding what is being said in the classroom, for example, here. And when the speech intelligibility is not good, it doesn't mean that people won't understand, because you have some part of words which are missing, but in the globality with the context, our brain will work to recreate the missing part of words, and then we can understand. But this process is very tiring. In fact, our brain is working, it's unconscious, but our brain is working to recreate the missing information, and then we understand, but we get tired. So after long hours of classroom, people get tired, really tired, and then we lose the good learning process. So the speech intelligibility depends on two main parameters. First is the reverberation, acoustic reverberation of the room, which is all the echoes in the room, but also it depends on the background noise level. So how reverberation can impact the speech clarity, the speech intelligibility. I will play here two short audios, and then you, with different reverberation, so you can hear how reverberation, acoustic reverberation, can affect the speech intelligibility. So first one is in a room with a high reverberation, and the second one in a room with low reverberation.
Many factors influence speech intelligibility.
Second one.
Many factors influence speech intelligibility.
So in both recordings, we can understand what is being said, but the first one with the high reverberation is not clear, and it takes a big effort to understand what is being said. In the second one, it's very easy, it's very clear. So on a long term, I mean, few minutes or hours of these two types of speech intelligibility. In the first case, we get very tired very easily, so we lose the concentration, we lose the students, for example. So on average, we know that we lose 30% of what is being said in a classroom when we have a bad acoustic, and it's not as extreme as the two examples I just gave you. It can be a very average acoustic reverberation in a classroom that conduct to this 30% of loss. So what we do when we design a classroom, or it can be a new project or a refurbishment, we do a modelization of the classroom, and we can predict what will be the speech intelligibility index. So we can play with different materials, we can play with their implementation and localization, and then we can adjust them to reach the highest possible intelligibility, knowing that the target is to get a high speech intelligibility everywhere in the classroom, not only in the front rows close to the teacher. So here is three examples of a very bad speech intelligibility, a bit improved with some treatment, and optimized with quite homogeneous intelligibility in all the classroom. Here is an example of it's a picture of a project we recently finished, and we can see the different materials we used. For example, here on the wall, we use a porous material that brings absorption in the high frequencies, and other materials on the ceiling that with perforated gypsum board that brings some absorption in the lower frequency. We have to know that sound is divided in different frequencies, and each material will bring some absorption in different frequencies. So in general, to get the right balance and the best speech intelligibility, we mix different material properties to get the right targets in terms of reverberation and then speech quality, speech clarity. And the last point, but it's very important too, is the noise from the technical equipment, because speech intelligibility depends on the reverberation of the space, but also depends on the ratio between the signal, the voice, and the background noise. So if we have a too high background noise, in fact, we reduce this ratio, so we decrease the speech intelligibility. So this has to be addressed, and ideally during the design phase, because it's quite easy to solve, controlling the airspeed in the ducts, for example, or implementing silencers close to the fans, technical equipment, and then it's easily solved. If it's not done properly at the beginning, it's always very complicated and very costly, because we need to change a lot of things, and sometimes we don't have the room, so it can be a big issue, but quite simple to solve when it's early in the design. So the canteen area is also a very important space, because it's it's the lunch break. It's a time where we should be able to rest and relax. And if we have a very noisy environment, it can be we cannot achieve these targets. So the main issues again here is the speech intelligibility, and also the high noise level we can get in these spaces. So here is a short video we recorded in a canteen we are working on at the moment on a refurbishment. So as you can hear, it's quite noisy, despite the fact that it's almost empty. I mean, there is not many students, and still we have a very high noise level. And the reason of this is due to the big volume and reverberation we have in this space. So just to finish on that. Again, if we get too much reverberation and a high noise level, we will lose the speech intelligibility. And this is, again, tiring. It's like when we all have this experience going to a restaurant with friends, and it's very difficult to communicate. It's very tiring. And this is not only due to the noise, it's due to the poor speech intelligibility, where we need to focus, and then naturally we speak louder, so we participate to the increase of the background noise. So here I give you an example of a project we had to work on. It was a canteen, a very noisy canteen, and the users were complaining about the high noise level and the uncomfort of this space. So they decided to ask a supplier to implement acoustic solutions. So they decided to change the ceiling and use an acoustic ceiling. So they were thinking that this would solve the issue. But at the end, it didn't change anything. It was still very, very noisy. So they asked us to study this problem and try to understand why, even if they have spent a lot of money on a new ceiling with acoustic properties, they didn't get any improvement of the canteen, in the canteen. And the reason is very simple. In fact, we did a study. So we calculated the reverberation time they had depending on the frequency here. So we can see the red curve, and they had a reverberation time around 2 seconds on average, and the targets, depending on the volume of the canteen and the use of the canteen, was around 0.9 seconds. So they were quite far from the ideal reverberation time for this space. So they implemented the new ceiling with acoustic properties, and we did a measurement on the reverberation they got. And in fact, this is the measurement we took in the canteen, and they only reduced the reverberation time in the low frequency, knowing that the speech, the human voice, is mainly in the medium frequency. This is the reason why they didn't get any improvement in the canteen. So again, this means that there is no one magic acoustic material that can solve all issues. In fact, it depends on the room, it depends on the materials, it depends on the shape and the volume of the room, and only by simulation and calculation we can know what amount of materials we should use and how to implement them and what acoustic property they should have. Some materials will be more efficient in the medium frequency or the high frequencies, and that's here what they should have used to solve the issue. So just to say that it's not there is no one magic pill to solve any issues. Here is an example of a canteen we did, and it shows the different materials we use. So here we used these bars that the designer wanted to use. So we used them as diffusers for sound. to spray the sound in all directions. We also use the property of the green wall they wanted to use. So this brings us some absorption in the low medium frequencies. We can see here we use acoustic ceilings with perforated wood and gypsum board to absorb the lower frequencies. We use porous absorber on this ceiling to bring absorption in higher frequencies. We use also on this part here behind the bars, but it's not shown on the picture. So the solution was to mix different properties of materials to reach the perfect balance in terms of reverberation, and then to control the noise propagation and the speech intelligibility. So to achieve this type of targets, we again use simulation tools. For example, here is a simulation of the implementation of a screen, acoustic screen. And so this calculation can help us to see how the noise will propagate after a different implementation of solutions, and then choose the best ones. Oh yes, I wanted to show you these two images because very often when we work on project, the designers and the client sometimes are a bit scared that the acoustic solution will kill the design, will be ugly material. So I wanted to show you this example. So we have on the left, we have the 3D renderings that the interior designer gave us at the beginning of the project, saying that this is what we need to achieve. And on the right, you have the picture of the project finished. So as you can see, the design intention is totally respected. And this is to show you that the acoustic design, if it's included into the design from the beginning, it's very easy to respect the materials, the intentions, the design intentions. This is how we do all our projects, understanding what is the intention from the designers, and then find the products with the proper acoustic properties that will reach both design intention and acoustic targets. So this is really possible, and it's what we do on all our projects. The music room is interesting too, because we have similar problems like the sound quality, clarity of sound, but also the insulation. So I will go through just to explain why it's a bit different. Because for the clarity of sound, the quality of sound, in fact, we can have different targets, and it's always very important for us to understand how the pedagogical approach is conducted, because depending on the reverberation targets we will have, it can change the behavior of students and teachers. So I'll show you these short videos of two different environments, one with high reverberation and the other one with low reverberation. So you can hear the difference, and I will explain why it's important. So we have a saxophone playing first in the reverberant room with high reverberation, and the second one is in a very dry room with almost no reverberation. So in the first case, we get a nice sound. It sounds really beautiful because we have all these echoes, but it's very difficult to hear all the small defects we can have in the sounds, especially for instruments like violin or saxophone, which requires a very precise way of playing. And in the second one, with no reverberation, it's very clear, it's very analytic, so we can hear, sorry, we can hear all the small defects. And this is important for us to communicate with the end user to understand the way of teaching, because if we use a very analytic room, a very dry room with low reverberation, okay, it will be easier to listen to the mistakes and correct the students, but it can be a bit discouraging because every time you play, the students will feel that they are not playing well, so it can be a bit discouraging. And on the other hand, if we have too much reverberation, everyone will have the feeling that they are beautiful players, but then they cannot correct and improve themselves. So the balance is most of the time between these two extremes, but it doesn't depend on us to choose the proper targets. It's really the choice of the pedagogical team. It's the reason we always try to have the communication, a clear discussion with them before choosing the right targets. And as acoustic engineers, in fact, we can achieve anything we want in terms of acoustic properties. The most difficult part for us is to understand the needs and define the proper targets. So for the installation part, I would say the approach is the same than the one we saw in the classroom. The difference is mainly due to the noise sources or sound sources. Music instruments can be loud, they can be have a lot of low frequencies, for example, which are more difficult to stop. So very often we have higher targets and heavier solutions to avoid the distractions between the two music rooms, for example. But on the overall, is the same approach. Maybe just the technical solution will be a bit different. So the theater area, it's an important part in the learning environment nowadays. So we have here three main acoustic issues: the quality of sound, the clarity of sound, the insulation between the theater and the external parts, but also the background noise, which is a big issue here, can be a big issue. So for the quality of sound, the main target will be to control the acoustic reverberation. But it's difficult here because, in fact, as you can see on this graph, every type of performance has its own targets in terms of reverberation. We don't have, we shouldn't have the same reverberation time for symphonic music or chamber music than for rock concert with amplification, or for the voice, for conference or movies. So we have this problem that the reverberation should be very different for each type of use and each type of performance. So ideally for theater, in terms of acoustic and quality, we should have a variable acoustic, but this is quite heavy, quite expensive, and most of projects don't have the possibility to afford variable acoustic. So our work here is to understand the priority and find a way to get the right target that will be the best compromise between all the targets that the school wants, and achieve something that will be as good as possible in most cases. But for us, this is the main issue. And again, once we know what we want, it's quite easy in terms of simulation and the tool we have to achieve the target. But the most difficult part for us is to properly understand the needs of the end user, of the clients, and define the proper targets. This is the most difficult part. For the insulation, in fact, what we want is to avoid the noise from the theater to go out and disturb other area, but also we need to protect the performance from external noise, as the silence is can be part of the performance. So it's very important to avoid to be able to hear any disturbing noise from outside. So the approach here is very similar to the music rooms or the classrooms. We do a simulation of all the transmission paths, possible paths, and we treat them. The main difference here is that, generally speaking, the volume is bigger. It's much more complex, so we need to address a lot of possible paths. But the principle, the way we do it is the same. It's a modelization, a 3D modelization of the space, and we address all the weak points, all the possible transmission. Then the background noise level can be a strong issue, knowing that in a theater we have a lot of people, so it means we need a big amount of air, so a big airflow, and this if it's not properly addressed from the beginning, can be a big issue, because it can bring a very high speed. So air speed. So we need to control this from the beginning to be able to properly dimension the size of the ducts, to control the airflow and the airspeed. Be able to implement silencers that can be quite big because of the size of and the importance of the airflow. And this is, I would say, easy to solve at the beginning because it's the early design. So we have the room, we have the space, we can ask for the space. But once the design is done, it's always very complex to ask to have a bigger room or change the size of the ducts or implement big silencer, because it has not been planned, and then we don't have the space. So again, this technical noise is easy to solve, but if it's not addressed properly from the early beginning of the design, it can become very complex. Okay, now we are going to speak about these big volumes we have in gymnasium and swimming pools. So the main issues are noise levels, because high reverberation and people doing sport, they can be loud. They need to shout and communicate a lot. Speech intelligibility is important too, because it's a learning environment. And in some cases, we can have the problem of the impact noise from the shocks on the floor. So the reverberation is a big issue because we have big volumes. We have a lot of reflective surfaces like water in the swimming pool, and then it can bring a lot of discomfort for the users, reduce safety in the case of the swimming pool, and also give some miscommunication. So we need to control that reverberation. For example, here it's a project of a swimming pool in the school we are doing at the moment. So because of the big volumes and the reflective surfaces, we need most of the time to use a lot of absorption surfaces. And in the example of the swimming pool, it can be even more complex because we have the environmental products like the disinfectants, like the chlorine or the humidity, that can affect the material. So we need to choose materials that can resist to these agents. So here we used on the walls, we use perforated bricks with a rock wool that brings absorption mainly in the lower frequencies, and we use suspended islands on the ceiling, porous materials, but the way we use it with a big air plenum behind them can bring absorption also in lower frequency and medium frequencies, even high frequencies, in fact. So this is an example. For the impact noise, especially when the sport area are close to sensitive space like classroom, we can have the transmission of the shocks in the structure of the building that can transmit the noise at long distance. So in that case, we need to use technical solutions like floating slabs that can avoid the transmission of the noise. And to finish, because I've been a bit long, I will speak about the library. Library, we have two main issues, distractions and noise propagation. So I go quickly because I'm over time. So the targets that here is a bit challenging, because in this space we need to have two things that are a bit conflicting. We need to be able to work together and communicate, so to have a good speech intelligibility, but in the same time we don't want to disturb others, so it means poor speech intelligibility. So this is a bit challenging because it's conflicting. So we use, again, simulation tool software that can allow us to predict how the noise will propagate, what will be the distraction areas around people talking, so to keep the good speech intelligibility at low distance and avoid long distance propagation. So this is the only way to succeed. Example here of a library we did with some different materials and implementation that can allow to control the noise propagation and the speech intelligibility. And to finish, I'm sorry, I've been a bit over time. Three things I'd like you to remember is, so we have been through different examples. Acoustic comfort is a key element in a successful school. The second one is that every area in the school has its own targets and then its own solution. So there is no only one magical solution that can solve all the issues. And the third thing I'd like you to remember is that acoustic design should be part of the design. It's not something that we can add at the end. This won't be efficient, it will be very expensive, and we wouldn't give the best results. So we need to think about acoustic design very early in the design process of the school. And so what we can say is that having a good acoustic comfort in the school will help to improve teachers' performance, will help to improve students' performance, and at the end, it will be the performance of the school that will be improved. So thank you very much. If you have any question about my presentation or the acoustic in general in the learning environment, you can contact me on WeChat, but also on LinkedIn, and follow us on our WeChat account. Thank you very much. I hope you enjoyed this presentation.